Time for the last chapter. Electrochemistry. Let's see. Okay. I might be able to finish it. We shall see. All right. Well, by now we ought to know what chemistry is. And electrochemistry refers to the types of chemistry that display a connection or an interchange between the chemical energy and electrical energy. And that invariably means electrons are transferred from one place to another. And that's how we gain access to the energy, by intercepting those electrons in some way so that we can use the energy that's being transferred. Now, we need some definitions here. And on the next slide, I've got this mnemonic. Rick. This is the term for oxidation. Oxidation is loss of electrons. So anything that loses electrons, whatever that species is, whether it's it's always not always, sometimes it's polyatomic. But whatever it is, it loses electrons in the process from reactant to product. And these two always occur together, oxidation and reduction. You can't have one without the other, because reduction is refers to the species that gains those electrons that we lost. Okay, they always go together. Now, when we have something that's been oxidized, whatever's oxidized is responsible for the reduction of the other reactant. So since it's responsible for the reduction, we call this the reducing agent. And vice versa, whatever is reduced is responsible for the oxidation of the other one. So we call that the oxidizing agent. Okay, just to get our terms straight. Oh, it's on this slide. My mistake. Okay. So when we have a set of reactants and products for a reaction, we've learned how to, actually in the first semester, we've learned how to balance these equations with the budget method. But sometimes the budget method doesn't work for oxidation reduction type reactions. It doesn't work well. Sometimes it'll work okay. But a more reliable way of balancing these equations is through an oxidation reduction method. And we're going to get there. But first, we have to be able to bookkeep the movement of electrons. Now, since some of these, those things that are oxidized and reduced, some of them are ions. And that's easy. If they're ions, then their oxidation state is just their charge. But some of them are covalent compounds. And they, by their very nature, don't have charges. But we need some way to track the electron movement. And that's where we use oxidation states. So these rules are what we use in order to fix certain oxidation states so that the others can be calculated. Excuse me. If we have an element, say we've got an we've got hydrogen gas and oxygen gas. I know where that leads. That leads to water. So we need, let's see, two here, two here. These elements, an element in its most stable form at room temperature and 1 atmosphere pressure is always given an oxidation state of 0. So we put that in the position where that we've reserved for charge. Anytime you have an element, that's the oxidation state. If you have a monoatomic ion, which we don't have here, you assign the charge. So an example for that would be if we have sodium metal and chlorine gas, we get table salt. Right, that's 2 here and 2 there. Right, again, that one's 0 and that one's 0. They're elemental. This is an ionic compound. We know the charge on the chlorine is -1 and sodium is +1. Those are the oxidation states for those ions. When oxygen is in a covalent compound, like water, we give it a -2 oxidation state. But we know that's covalent compound. That's not a charge. Okay, that's where sometimes we can get mixed up. Which means what for hydrogen? Well, hydrogen would have to be a +1 in order to balance the oxidation states. Now, the other possibility for oxygen is if you find it in a peroxide, and the simplest peroxide is hydrogen peroxide on your medicine, in your medicine cabinet. We would draw it like this and like that, and this group has an oxidation state of 2-, so each one of these is a minus. Okay, so that's the exception. When we have a peroxide, each oxygen is a -1. Hydrogen in a covalent compound is +1. Sometimes hydrogen occurs in ionic compounds. If we form a hydride of some metal, like our example here is aluminum hydride. And so we have aluminum, and then we have 3 hydrogens. The aluminum is a metal. We have to give it a positive oxidation state. So it's a +3. That means that hydrogen is a -1. And so whenever you have a compound that's metal hydride, that's a -1 for hydrogens. We could do it with any of the other metals. Magnesium hydride, lithium hydride, they all give hydrogen a -1 oxidation state. Fluorine is the only halogen that has an absolutely fixed oxidation state. Right, so fluorine in any compound, simplest, we might be like that. So this would be a -1, that's a +1. So fluorine in a covalent compound, or ionic compound for that matter, is always -1. That's the only possibility. You'll notice in your periodic table that comes with your review document that there are multiple charges that you see in each one of these squares. Those, it depends on the situation as to whether they're an actual charge or an oxidation state. If you see chlorine in an ionic compound is going to be -1. But in a covalent compound, it could be a number of different ones. And sometimes we have to make assumptions about the other halogens in order to calculate the oxidation state for whatever its partner is. And we'll run across some examples of that in just a minute. Okay. Summation of the oxidation states for neutral compounds, whether they're ionic or covalent, must be 0. So you have to add up the oxidation states. Here we would have 2 times +1 is +2. And 2 minus that yields 0. If you have a polyatomic ion, like nitrate, right? The summation of the oxidation states must be the charge. So if oxygen, we take oxygen as -2, so -2 times 3 is -6. Well, what would give you a negative charge for nitrogen? There's only one of them. So a +5 and a -6 equals -1. Right? But it has to add up to the charge on the polyatomic. All alkali metals, we give those +1 charge. We learned that from nomenclature. All alkaline earths are +2. I'm not sure about boron, but aluminum, gallium, and indium are always +3. Depends on what boron is paired with. If it's right, because it's right on that border. If it's in a covalent compound, then you probably have to calculate it. If it's in an ionic compound, it's probably +3. When chlorine is in, I mentioned this earlier. Sometimes we have to calculate the values. And if we end up in a situation where we have something like this, we don't have a rule for this one. And in order to, sorry, let's put it up here. We don't have a rule for that one because the only halogen we've fixed is fluorine. So if we don't assume something for chlorine, and that's usually the way you go for the more electronegative, then we have to say this is -1, which is a +5 total. That makes this one, wait a minute, is a -5. This makes phosphorus a +5. And that's okay because this is a bookkeeping scheme. We're just trying to keep track of our electrons. Nitrogen in, say, cyanide, okay? Well, which one are we going to fix? Well, carbon is one of those that can be +4, +3, +2, +1, 0, -1, -2, -3, -4. It can be all of those. So it's safer to go for the more electronegative nitrogen and say, in this case, it's a -3. And that makes this one a +2. +2 and -3 is -1. Okay, so here's some examples. Let's make some room. See if we can figure these out. For potassium dichromate. All right, which ones do we know? We've got rules for the potassium, that alkali metal, and we've got a rule for oxygen. Right? So 7 times -2 is -14, and 2 times +1 is +2. So what we have here is a -12 in that balance. So that means those two chromiums have to balance out that -12 with a +12. +12 total, which means for each one, it would have to be a +6. Okay. Now we have a carbonated polyatomic ion. Okay, we have a rule for oxygen, -2, and that's a -6 total, but we have to be sure that there are -2 left over. So we really only have to balance -4 of those. That makes a +4. Right, so a -6 and +4 is -2. Okay. I'm gonna keep going. Manganese. Manganese 4 oxide. So this is a -2, that's a -4 total. This has to be a +4. We've done some of this already in nomenclature. Is this type 1, type 2, or type 3 compound for naming? Can manganese have multiple charges? Yeah, it's a transition metal. So they're only, remember way back first semester, which ones of the transition metals have fixed charges? Silver, cadmium, zinc. They would give you a type 1 compound. All the rest of them give you type 2 compounds, which means we have to say what it is. So we'd say manganese 4 oxide. That'll be your name. Okay. All right. And those are the charges. PCl5 we did already. Right, +5 and -1. How about the last one? Type 1, 2, or 3. Sulfur and fluorine, both nonmetals. So it has to be a type 3. So we would just say sulfur tetrafluoride. But for electrochemistry purposes, the fluorine we fix as -1. That means sulfur has to be a +4. Oxidation state. There we go. Okay. Now we're going to get into balancing these equations with what's called the half reaction method. Since in electrochemical reactions, oxidation reduction reactions, or we abbreviate them sometimes redox. And I emphasize this point again. This is just an example of nature doing what it does. All this happens simultaneously. And what we're doing is we're splitting the reaction apart into its reduction steps and oxidation steps so that we can make sense of it, keep track of the electron movement. Okay. So this particular balanced equation where we have 8 hydrogens, what does that tell you about this reaction environment? It's acidic, right? If you've got those hydrogens in there, it's acidic. And 1 manganate ion plus 5 iron 2 plus yields manganese 2 plus, iron 3 plus, and water. So if this equation is balanced, which steps are reduction and which are oxidation? Well, what we've done here, just to illustrate the half reactions, we've split out the reduction step. We've taken manganate ion and the manganese 2 plus ion on the product side, and we show that it is reduced. And when something is reduced, the electrons go on the reactant side because they're being added to something on the reactant side, and they don't show up on the product side. So they have to be in something that was on the reactant side. Okay. And vice versa, the oxidation step shows the electrons on the product side because they're being released from whatever was on the reactant side. And notice that the number of electrons during the oxidation step and the reduction step has to balance. Got to have the same number of electrons. Because in chemistry, we don't build up static charges. That's physics. They do that all the time. But we don't like to build up static charges in our reactants, our reaction vessels. It's not cool. Okay, so this would be the split of the reduction step and the oxidation step. And if you add those two together, you get that target equation, the first equation. Okay, we're going to do one ourselves in just a second. Okay, these are the rules. This is how you do it. And then I'm going to show you an example. You take what you're given as reactants and products, and you look at their oxidation states of each of the elements, and you decide based upon their oxidation state changes, which one is the reduction and which one is the oxidation step. And then you separate them out. And then you look for anything but hydrogen and oxygen, and you balance those elements first in each of the steps, the oxidation and reduction steps. Then you look for oxygens and you balance the oxygens and with water. So if you have 2 oxygens on one side and you need 2 on the other side, you have 2 waters. That means you've added hydrogens, 4 hydrogens. Then you put 4 hydrogens on the other side. Okay, it'll become clear once I start doing it. Then you can balance the electrons. Actually, you can balance the electrons before you do all this, but this gives you some order. Then you match the number of electrons for each of the steps. Whatever you have to do, multiply, divide the whole equations, the whole half steps, so that the electrons balance. And once the electrons balance, then you can add the equation back together. And that should be a balanced equation when you do that. Okay, and this is a flow chart, if you like flow charts. Okay, here's an example. Let's balance this equation using the half reaction method. Dichromate in aqueous solution, and then sulfite in aqueous solution yields chromium 3+ ion in aqueous solution plus sulfate. So everything's happening in aqueous solution. So what's wrong with this equation? I'm sorry? Well, yes, that's obvious. We're missing cations, right? You don't have anions by themselves. This would have to be something like potassium dichromate or sodium dichromate in solution. This might be sodium sulfite or potassium sulfite and so forth. And this might have an anion with it. What we've done is we've removed the spectators. We don't need the spectators. They just muddy the water. So get used to that. Okay, so now we need to separate into oxidation steps and reduction steps. So the first thing you have to do is determine the oxidation state of each of the elements, right? This one's 3+ by definition. Let's work this one over here. -2 for the oxygen, which is -8 total, right? But we have to keep 2 of those negatives out. So we really only have to balance a -6. That means that sulfur is a +6. Okay. All right, let's move that so we can do some more. How about this one? Well, 3 times -2 is -6, right? But we only need to balance 4 of those. So that's a +4 here. Right, the +4 and a -6 is -2. And this one is, let's see, -2 times 7 is -14. And we hold 2 of those out to keep the negative charge. So we're balancing a -12 against that one, which is a +12, but we got 2 of them, so each one is a +6. Okay, now we have our oxidation states. Sometimes I draw tie lines, helps visualize things. What is changing? This chromium is going from +6 to +3. How do you do that? You can't change protons, that's your positive charges. You have to change electrons, right? So we would have to add 3 electrons per chromium to get to that 3+ state, wouldn't we? 6+ and 3- is a 3+. So that is what? We added electrons, that's the reduction step. And I'm gonna put that there. And I'm gonna leave the aqueous out because the whole thing's in aqueous solution. And this yields chromium 3+. Okay, we'll come back to that in a second. That's left over. Now we have the sulfite with a +4, and it's being oxidized. It's going from +4 to +6. That means the oxidation number increased by the loss of electrons. So we lost a couple of electrons to get from sulfite to sulfate. Okay, now we've got our we've got this split into half reactions. Balance the non-oxygen, non-hydrogens. 1 sulfur, 1 sulfur. We're good. 2 chromiums, 2 chromium. Okay, now we do the oxygens. So we have 3 oxygens on this side and 4 on that side. Which side does the water go on? This side. Right? 1 + 3 is 4. So we added 2 hydrogens. So now we have to put 2 hydrogens on this side. Okay. All right. So now we go back to this one, say we have 7 oxygens on that side, none on that side. That gives us 7 oxygens. But we've got 14 hydrogens added. Okay. All right. Now we're going to do the electrons. If this is the oxidation step, electrons go on this side. So how many of them were there? Well, for each sulfur, there are 2 lost from this side. On this side, we have going from +6 to +3, we've gained 3 electrons each. But there are 2 of them. So that's +6 electrons. Okay. Now that we've got our half reactions balanced, we have to reconcile the number of electrons. This one has 6, that has 2. How do we make this one 6? Multiply by 3. So we'll take 3 times the whole thing. Right? Once you've got a balanced equation, the ratios are fixed. So you can multiply the whole equation through by some factor, and it doesn't change the ratio. So this puts 3 here, 3 here, a 6 here, 6 there, and a 3 here. We used up that 3. Now we can add them together. Now we can bring the electrons down if we want, but they're going to cancel anyway, because we set it up that way. Those 6 electrons cancel these 6. And then I'm going to try to bring them down in this order. So I'm going to put dichromate first. Okay. And then I'm going to put sulfite. Here, 3 sulfites. Okay. Then I'm going to bring down, say, the waters. So we have 3 waters here, none on this side. Okay, use those, and 14 hydrogens. Now we have 1, 2, 3, 4. 1, 2, 3, 4. Now on this side, you start off with 2 chromiums. And then we have 3 sulfate. Then we have water. And then we have hydrogens. 1 plus 6 hydrogens. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So we've got water on both sides, and we've got hydrogens on both sides. So we got to reconcile that one. We got 7 waters over there, 3 over here. So if we subtract 3 from both sides, gets rid of that one and makes this one 4. We have 14 hydrogens on that side and 6 on this side. So if we subtract 6 from both sides, we have 8. There. There's your balanced equation by the half reaction method. And these subsequent slides go through each one of those steps one at a time. And let's see. 3, 8, 2, 3, 4. Okay. You have to be extremely, now I hesitate to use the word, very methodical. Let's put it that way. Stick to your method so that you don't get off the beaten path. Okay. Now, I will say that this is the half reaction method, the acidic half reaction method, because we're only dealing with H pluses. But we know that some reactions, redox reactions, balance in basic solution. So I'm going to skip ahead here and tell you, what do you do if this one is given to you and say balance it in basic solution? You do the acid first, then you neutralize your hydrogens with hydroxides. So if I put 8 hydroxides on this side, I have to put 8 hydroxides on this side. Okay. So what do I get out of that? A hydrogen plus a hydroxide is water, correct? So we have 8 waters on this side, and we have 4 on this side. So now those waters go away, and we have 4 waters left on this side, and 8 hydroxyls. So balanced in basic solution would be the dichromate, 3 sulfites, 4 waters, 2 chromium 3 plus, 3 sulfates, and 8 hydroxides. That would be what I call the fake acid method, balancing in basic solution. Now, always remember that all of this stuff, at this point, we've got all this stuff together in the reaction vessel. We haven't separated them yet. We're going to, but we haven't yet. So at this point, we just put these things together, and that's what happens. In acidic solution, it was the one before. In basic solution, it's this one now. Technically, you should be able to go directly to balancing in basic solution. Just work with hydroxyls. But as a practical matter, it's more difficult. So we do the acid first and then change it to basic. Okay, here we have another example. In acidic solution, bromide ion, manganate ion yields bromine, elemental bromine, and manganese 2 plus. So rather than put those on the board, oh, I guess I should have, right? Because I don't have it split out. So let's do that one. There. And let's see, this is aqueous. And we have the manganate. And again, we're missing our cations. Right, plus manganese 2 plus aqueous. All right, so that's a 0. That's a -1. This is, let's see, -2 times that, -8. And we only need to balance -7 to hold one of those out. So that's a +7. And that's a 2 plus. So our oxidation step is which one lost electrons? If we go from a -1 to a 0, we had to lose 1 electron. So this is our oxidation step. The R2. That means this must be the reduction step. MnO4 minus 7 plus. And that goes to Mn2 plus. That makes sense. For each manganese, we picked up 5 electrons. Okay. Balance the non-oxygen hydrogens. Just put a 2 there, we're good. And manganese, we're good there. We don't have to worry about oxygens, hydrogens up here because there's nothing to deal with. But we do have 4 oxygens here. So that's 4 waters, which means 8 hydrogens over here. Now we can do electrons. If this is the oxidation step, we lost 1 electron per bromine, but there are 2 bromines. So we actually lose 2 electrons in that process. We go from a 7 plus to a 2 plus. We had to add 5 negatives, 5 electrons to go from 7 plus to 2 plus. Okay. Now, how do you reconcile a 2 and a 5? Right? They're both prime numbers. They're not multiples of each other. Go back to math. Cross multiply. Let's say 5 here, 2 here. That'll give you 10 there, and that'll give you 10 here. Okay, so 5 times 2 is 10, and 5, and 10. Use that one up. This is 10, and 16, and 2. Let's see, let me make room for that. There we go. And 8, and 2. So now we can add them together. So I'm going to try to keep them in order. Bromide ion. Okay. And then I'm not going to bring the electrons down. Then 2 manganate ions plus 16 hydrogens. And so that's 1, 2, 3. 1, 2, 3. And on this side, we'll start with 5 bromine and 2 Mn2 plus and 8 water. And we can't reduce it any further because we got odds and evens. And there's no imbalance of hydrogens and waters from either side. So that's our equation. Right there. Let's see. Oops. Forgot that. NBR 16 hydrogens, 2, okay. 5Br2, and 8 waters. Okay. Now, how would we make this basic? Add 16 hydroxides and 16 hydroxides, and then cancel the waters. Okay. And this is just step by step for the fake acid method. You do the acidic balance first, and then you neutralize the hydrogen ions with hydroxyls. And this flow chart simply added those 2 steps at the bottom in green from the previous acidic balance half reactions. This just draws attention to the fact that we could possibly balance this thing in using hydroxyls first. If you add hydroxyls first instead of hydrogens, what are the potential problems? Well, you have to add water to the other side to compensate for oxygen in addition of hydroxyls. But then you've also added more hydrogens. So then you have to balance the hydrogens again from one side, and you just flip back and forth until hopefully you get a balance. Right. So balancing with the acid followed by the basic is the most efficient way to proceed. Okay. What am I doing here? Balance the following in basic solution. Okay. This should be fairly simple since we've already done one. Okay, cyanide. That's a fun reaction to process. Oops. Looks like capital, doesn't it? MnO4 minus. Okay. MnO2. O2 solid. Okay, so we need the oxidation and reduction steps. All right, what are we going to do with this one? Well, we did that before, right? We give nitrogen a -3. So we only have to balance a 2+. And this one we did before is +7, I think. Is that right? -8, yeah, +7. This one, the oxygen is -2, -3, which is a -5. But we only have to balance a -4 to keep that negative. This is a +4. And we did this one before. Minus a +4. Okay. So the oxidation step, we go from +2 carbon to +4 carbon. Okay. And the reduction step should be the manganate ion at +7 goes to manganese 4 oxide. Okay. So now we balance the carbon's balanced, nitrogen's balanced, manganese is balanced. So now we go to the oxygens. We need 1 oxygen on this side. And that puts 2 hydrogens on this side. Okay. We got 4 oxygens here and 2 over there. So we need 2 more oxygens on this side. That means 4 hydrogens on that side. Electrons. We're going from wait just a second. Did I do that right? Oh, transposition error. Here we go. Now it makes sense. All right, oxidation. So we lost 2 electrons that show up over here. 2 electrons for each carbon, and there's only one of them. On this one, we added 3 electrons to go from +7 to +4. Now we can reconcile, right? We've got an odd and an even, so that means cross multiply. That's 3 here and 2 there. This is going to be 6, 6, 3, 3, and 3. This will be 8, 2, 6, 4, 2. Now we can add them together. Right. Electrons are going to cancel. And we'll just bring down 3 cyanide and 2 MnO4 minus and 3 water and 8 hydrogens. Let's see, that's 1, 2, 3, 4. 1, 2, 3, 4. Then we have 3 CNO minus and we have 2 MnO2. And then we have 4 water and 6 hydrogens. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Since we're gonna make water by neutralizing the hydrogens, let's just balance the hydrogens first. Right, 6 there, 2 here. That means we need 2 hydroxyls, and we'll deal with the waters later. That means 2 waters here and 3 waters there. So that's 5 waters on this side, 4 on that side. Those waters go away. And this one becomes 1. Okay. But we'll pull that one over. So we should have 3 cyanides, 2 manganetes, 1 water, 3 CNO minus, 2 MnO2s, and oops, I forgot to put the 2 hydroxyls on this side. We added 2 hydroxyls there. I'll let those out. 2 hydroxyls. And that's a basic solution. Okay, up to this point, we've had everything in one big boiling pot. As Mammy would say, Gone with the Wind. Have you seen that movie? Let's put the clothes in the boiling pot. Crawling crow, clothes, and dysentery. That's what she said. So we put the clothes in the boiling pot. I can't remember the actress's name. She got an Academy Award for it. Supporting actress. Okay, so now these reactions are accurate, balanced in one vessel. The problem with that is when those electrons move, we have no access to them. We can't get at those electrons to extract the energy that they are transferring. So the galvanic cell is an attempt to do that. We separate those half reactions into separate vessels, and we make an ionic connection between the two with an external loop that carries electrons. And that's where we intercept those electrons and use them. Like to do that. or to heat the building or run the air conditioner. That's called a galvanic cell. Now, galvanic cells, named after an Italian, Galvani, they intercept those electrons in a spontaneous redox reaction, which means we put those reactants together, either in the same vessel or connected ionically. The reaction is going to go. We don't have to do anything. It just goes. Another word for this is a battery. The reactions occur at the electrodes. So if we separate these reactions into two containers, wherever the electrode enters the solution that carries the electrons from one side to the other, that's where the reaction occurs, at the electrode. Here's an example. So if we have these two vessels, one on one side and one on the other, one has the oxidation reaction in it, the other has the reduction reaction in it. And then in order to get electricity to flow, you always have to have a circuit. It has to be a complete loop. So part of that loop is facilitated by the salt bridge, which is what we would do in the lab. Or if you have a set of vessels that are connected by a porous disc, that works good too. In fact, it's better. The salt bridge introduces what we call internal resistance to the movement of ions, whereas the porous disc is not as impeding. And then the electrodes are those strips of metal you see submerged in the liquid. And the pathway for electrons is through that external wire. And that's where we would hook up our voltmeter so that we can measure the voltage between the two cells. Okay. We have to have a salt bridge. From an electrical standpoint, it's to complete the circuit. From a chemical standpoint, it allows the movement of cations and anions without the wholesale mixture of the contents of the vessels. That way that we can keep the solutions neutral. Because when you move electrons from one side, if you move electrons from this side, right, move electrons from this side to this side, and if we were able to do that, we would build up a negative charge on that side and a positive charge on this side. So we put a salt bridge in here that only allows ions to move, not electrons, ions. They could be monatomic, they could be polyatomic. Most of the time they're monoatomic. And that way, we can replace the negative charge on this side and neutralize it on this side. Now you can make that salt bridge different ways. You can have a liquid in your loop, and you just plug the ends with something. But we're gonna make a potassium chloride salt bridge with agar, and then we're going to squirt that hot agar solution in here, and it solidifies, and that keeps the wholesale mixture from occurring, but allows ions to move. Porous disc, okay, it accomplishes the same thing. Now, typically when we diagram these galvanic cells, we put the cathode on the right. Oh, definition time. Cathode is on this side, anode is on this side. Definition is, this is the site of reduction. So if electrons move over here, they're going to come out here and reduce something. The anode is the site of oxidation. So we're going to move electrons this way, and something's going to lose electrons on that side. Okay, that's by convention. We put the cathode on the right, the anode on the left. Okay. Now, what do we mean by cell potential? That shouldn't be there. I got my animations out of order. Cell potential is voltage. Cell potential is sometimes written with that curly E, which is in volts. Or if it's really, really small, millivolts. Think of electrical potential or voltage as a push. What's pushing those electrons over here? It's the voltage, right? And the higher the voltage, the bigger the push. So for these types of cells, what the dry cell that you put in your flashlight is 1.5 volts. That's pretty low voltage, but it accomplishes the purpose. In your car battery, you'll have 12 volts. That's a little stronger, right? And if you grab both electrodes, you're going to feel a shock. In fact, it's not just the voltage that affects your nerves. It's the amperage. That is how much charge is being moved. Right? What do they say? When you get struck by lightning, it's not the voltage that kills you, it's the amperage. It's the movement of massive amounts of electric charge through your body. That stops your heart. And I guess if it's strong, it's strong enough, it's like 1,000,000 volts. It can fry your organs while on the way through. Because there's resistance in your body. Resistance primarily from water, because pure water is an insulator. Pure water does not conduct. The only reason that you can conduct is because you have dissolved salts in your system. And you have to be grounded, right? If the ground is positive and there's a buildup of negative charge in the cloud, then when it discharges, those negative charges go like that, and they want to find the shortest distance with the least resistance to the ground. Right? And if you're standing out in the open with your feet in a puddle of water, you're a prime candidate. That's why when they electrocute somebody, they take that sponge and wet it, slap it on their head before they put the electrode on. It's a better conductor. And the water will become conductive if it's ionized. And the size of the voltage, the size of the electrical potential can ionize water. If it's a huge voltage, like 20, 40,000 volts, then it will ionize, and then it becomes conductive. But low voltage, like 1.5 volts, if you put the electrodes from a battery and with a light on the outside, and you put those in water, it won't light. If you put some salt in it, it lights. I knew this, I didn't know her very well, but I went to school, high school, with a girl. This was a private school. My father was a teacher, so we got a break on tuition. Teachers being poor, we couldn't afford to go to this private school. All we had to buy was books and uniforms. But this girl came from a wealthy family, which is most of the kids in the school. And they had a summer cabin north of Atlanta. And she went up there to spend the weekend. She drew a bath, hopped in the bath, and got on the telephone. And in those days, no cell phones. So there was a hard line, in a thunderstorm. That telephone line got struck. It went through the telephone, in through her, into the water, into the ground. And she died. Okay, cell potential. I guess you can I like to think of electrical potential as a push rather than a pull. I'm with Einstein on that. Einstein never could reconcile himself to the concept that two objects, two large bodies in the universe would attract one another. He just couldn't wrap his mind around pulling together, right? That force. He thought it was more logical for something to be pushing them together. And he eventually came up with an explanation. Right? His general theory of relativity said that those large masses actually curve space. So when this large mass curves space and that one curves space, then the curvature causes them to follow the path, not a linear path, but the shortest path would be around that curvature, and that brings them together. So they're being pushed together by the curvature of space. Well, I think of electricity the same way. These batteries, these galvanic cells, electrons are being pushed from one side to the other. Okay. I don't know why I left that in there, because I like push better. But there's a driving force for, and it's often called the electromotive force, EMF. And this occurs as a consequence of a spontaneous electrochemical reaction. And that's the volt. Now, the volt, by definition, 1 volt equals the amount of energy required to move or obtained from the movement of 1 coulomb of charge. So it's 1 joule per coulomb. And a coulomb is a unit of charge. Right? There's a conversion factor between coulombs and moles of electrons, and we'll get it in a second. This is a coulomb. It was a convenient unit of measure when electricity was being investigated back in the early 19th century, and it stuck. Oh, we got okay. I'm not going to bother trying to get the sound to come through here. What I've discovered is if I do that, then it messes up the recording. So we'll just tune our ears, and when I process the video, I'll put the original in there, and no problem.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt ridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
And if we ever make it to the lab, that's the reaction that we're going to be investigating. I was just thinking, what's the electronic configuration of neutral zinc? 30. All right, so we got argon core. You remember this. And then we have 4s, 4s2 and 3d10, right? Yeah. Okay, so when zinc loses electrons, it prefers to lose these two right here. These are the valence. That's the valence shell. So if it loses those two, then it's got this configuration, 3d10. And a complete D shell is more stable. When copper, let's see, copper is 29. So it would just be 4s2 and 3d9, right? Well, actually, it's not. One of those oddballs, if you recall. Its neutral is 2, excuse me, 1 and 10. So when it gains an electron, let's see. Oh, it would have to be copper 2 plus, because it remember the solution in there was sulfate, so that's a 2 plus. So what would this 2 plus be? Well, it would be that one and this one. It wouldn't be this one. So it wants to pick up those 2 electrons, and by doing so, it makes this and this. D10 is more stable. Okay, so when zinc is oxidized and copper is reduced, that's the consequence of that movement of electrons. All right. So we've got the outline for a galvanic cell. How do we measure that cell potential? Well, there's several ways. There's the cheap way and there's the expensive way. The cheap way is less accurate. The expensive way is more accurate. The cheap way is use a voltmeter. Right? The voltmeter has a standard resistance in the circuit. So it measures the movement of electrons against that resistance, and we'd have to go back to, let's see, physics. Let's see. Cap I. To Ohm's definition of resistance, which would be volt per current, and this is amperes. And that's volts. So if this is fixed, then we have a circuit in there that will measure the movement of electrons. Okay, and it electronically plugs these values in here and here and calculates V. So this would probably be better. This is constant. So as the amps go up, as the current goes up, voltage goes up, and it displays that in the meter. That's the cheap way to do it. The problem is maximum cell potential is only measured when there's no current. Nothing's moving, right? Because when something's moving, then you're you're losing some of that voltage to internal resistance. So the accurate way, the more expensive way, is to use a potentiometer. And what a potentiometer does is it has a source inside the device that provides a reverse voltage. So when you're measuring the voltage of an external circuit, the internal circuit, you adjust it to where you stop the current moving. And when you do that, then the device reads out the amount of voltage required to stop the current. And that measures your voltage. That's maximum potential. Because when you get to that point, nothing's moving. So by definition, that is the maximum potential for the cell. And as well, the business model, the capitalist model is it's more accurate, so it's more expensive. We usually only have potentiometers in research labs. Voltmeters, or now they call them multimeters because they'll do a whole bunch of stuff. You can get for less than $10 at Walmart. Okay. So this digital voltmeter is put in the circuit, the external circuit, so it can measure the voltage in that circuit that is being pushed through the external circuit. We insert our meter there. So as a practical matter, when you set up your galvanic cell, you can construct the cell right down to immersing the electrodes in the solutions and putting in the salt bridge. As long as you break that circuit, then you're getting no chemical reactions. Right? It's when you connect the circuit, then the electrons start to move and you can measure your voltage. Okay. Now, what's a standard reduction potential? Well, what we want to be able to do is to say, all right, hypothetically, if I want to put this cell together and I want to reduce something on this side, and I've got an idea of what I want to put in that solution to accomplish a reduction, and I put the oxidation in this side of the anode, and I say, okay, I want to put those together. What can I expect for the voltage? Is that a spontaneous reaction? Will it go this way? Or if I mess up and I put the wrong combination together, maybe it's going to go this way. Well, I want to know before I build that thing whether it's going to go this way or that way, and how much. What's the voltage going to be? Expected voltage. Well, the way we do that is to determine experimentally what are the reduction potentials for every reaction against some standard. Right? Because you're not going to get any measurable voltage if you only have a half cell. Half cells don't produce voltage. Only whole cells, where you have two halves put together. So what we do is we convert one of those cells into standard hydrogen electrode. So what's going to happen to that gas? Well, if it's on this side and it loses electrons, what happens to hydrogen when it loses electrons? It becomes positive, right? Okay. So that hydrogen gas plus something over here is going to yield those ions. And if we measure that potential, standard reduction potential, that means on this side, with this as the anode, the hydrogen, standard hydrogen electrode is the anode. What voltage will it produce against that electrode? Now, in electrochemistry, if the potential is positive, that is spontaneous for a complete cell. So if we run this against that, we get electrons moving that way, that's a positive voltage. But if we happen to put this together with that, and we get a negative voltage, in other words, electrons move back this way, and we take hydrogens from here and make hydrogen gas, then that is non-spontaneous in that direction. But it's spontaneous in this direction. So what does that mean? If we got a negative voltage, now this is the cathode and that's the anode. Okay. So researchers have created tables, and you've got one in your textbook and in your review document, table of standard reduction potentials. Okay. Now, what's required for a standard? Well, the solutions have to be 1 molar, and any gases introduced have to be under 1 atmosphere pressure. Okay. And at 25 degrees Celsius. So there they are. They're compared to the hydrogen electrode. And by definition, the hydrogen electrode is given as 0 volts. So you compare this 0 volts to whatever you get here, and that's what you assign to this one, either positive or negative. Hydrogen is by definition given a 0 voltage. All right. So when we standard conditions, right, the sign is reversed from positive to negative if the half reaction is reversed. So if we have a half reaction where we have reduction, so we have something over here plus electrons yields something over here. I don't know. That's the way it's written with the electrons on the left-hand side. Standard reduction potentials. And then a value here is given. So it's either positive or negative. And another point is that this potential is an intensive property. It doesn't matter how much of this metal you have, how much of the electrode you have, how much solution, what the concentration of the solution is in your proposed cell. The standard is based upon 1 molar, so it doesn't matter. Okay. Okay, I've just given you the fact that positive value is spontaneous, negative is non-spontaneous. And actually that's it's like grandfathered in from a mistake that was made early on when scientists were studying electricity. They believed that the charge carrier was positive. So they went from positive to negative to define current, but it's actually the other way around. So we're kind of stuck with it. So what we have to say is this positive value is spontaneous. And then if we want to make conversions to energy units, right, we have to introduce our fudge factor. negative, like we've done before. Okay, so here's the first part of that. You see the whole thing is in your review document, and I've just broken it out so I can expand it a little bit. But if we start with fluorine against hydrogen electrode, that fluorine is definitely going to be reduced. It's a positive value. In fact, in our table, it is the highest electromotive force against the hydrogen electrode is 2.87 volts. So that's what you should get. If you have a standard hydrogen electrode and fluorine in this side being reduced to fluoride. So we would pump fluorine in here at 1 atmosphere pressure, and it would be converted to fluoride by reduction and give you 2.87 volts. Silver is a little less, right? 1.99 volts against a hydrogen electrode, and so forth. And they're ordered so that the reduction potential decreases as you go down. And we'll get to a point here, there, where hydrogen against itself is going to be 0. Okay. Now, iron 3 plus going to iron by reduction is negative. So if you put iron over here, 3 plus iron here, and an iron electrode there, it's going to go that direction. And we'll get down to lithium. If you guys wanted to be chemists, we would have an activity table for metals. And the more active the metal, the more likely it is to be oxidized. In other words, to lose electrons. So that lithium at the bottom with a negative voltage of -3 means it is the most active metal in there. It wants to go the other direction. Okay, it's the most active. Potassium is a little less active. Let's see, we move on up. Aluminum is less active than that. Zinc is less active than that. But zinc is more active than copper, because if we go back up to copper, go back up to copper here, 0.3 volts, 0.34 volts. It goes this direction against a hydrogen. Zinc goes that direction. So when we put them together, what should happen? If we put zinc and copper together on either side, we should get zinc being oxidized. So zinc would be over here, and copper would be over here being reduced. I'll show you how to calculate those in just a second, if you haven't already peeked ahead. Now, your book is going to tell you, if you want to find the standard, which is E0. E0 is standard. Standard conditions. You want to find the E0 for a cell, you look at your table, you find the standard potential for the cathode, and you subtract the potential for the anode. But I've got a more reliable way to do it. I mean, you can memorize that if you want. But you have to decide which side is the cathode and which is the anode. What you want is to construct your galvanic cell so that you get a positive potential. That tells you which way it's moving. And in order to do that, you take your half reactions, like say zinc plus 2 electrons yields, wait a minute, yeah. Zinc 2 plus electrons gives you zinc, and copper 2 plus 2 electrons gives you copper. Okay, so let's look at the values. What are the standard reduction potentials that go with those reactions? Let's see. Where's copper? Copper. There it is, copper 0.34. So this is 0.34 volts. Reduction potential against hydrogen electrode. Zinc is minus 0.76, minus 0.76. Now, you can't build a galvanic cell with that reaction and that reaction. One of them has to be reduction and the other one has to be oxidation. So which one are we going to have to flip so that the summation of those standard voltages gives us a positive value? If you flip this one, the voltage now is negative. Right? That's not spontaneous because a negative and a negative is a negative. So if you change this one to positive, in other words, you flip it this way, zinc yields zinc 2 plus 2 electrons yields a positive 0.76. Now, when you add these two together, you get a positive voltage. Let's see, that's 0, 1, plus 1.10 volts. Now, what does that make for our cell? This is the oxidation step. This puts zinc. Let's put zinc on this side. And it puts copper on this side. Because copper is the one that's being reduced. Okay? That's how I do it. And you can't make a mistake. That formula is correct, but just like anything, if you memorize a formula, you better be sure you got the variables in the right place. But this way, I reason it out and I always get it right. Okay. So let's see. How about this one? Let's see. Let's make some room here. Messed up a little bit there. That one, I'll leave that there for now. Okay. For this example, we have a reaction. If we put this in one big vessel, then the reaction is going to go until we run out of one of our reactants, right? Whichever one is limiting. So if we have enough iron 3 plus ions, then we can completely consume that copper, that piece of copper metal. But if we don't have enough iron, then it's going to be limiting. And eventually the reaction will stop. But if we separate them, how are we going to separate those? Well, iron 3 plus to iron 2 plus is what? It's reduction, right? Iron 3 plus an electron yields iron 2 plus. And the other one is copper. This is an oxidation, yields copper 2 plus 2 electrons. Okay. There's your half reactions. This one is 0.77, 77 volts. The copper, if we write the copper as a reduction, it's 0.34. But this is an oxidation, so that's negative 0.34. So that's a positive. If we put these together like that in a galvanic cell, it's going to be spontaneous. Okay. Now, balancing the equation is one thing, right? We need 2 electrons, so we'd have to have 2 here, 2 here, and 2 here. And 2 electrons actually move in that reaction. That's important to remember. How many electrons move? The reason you need to remember how many moles of electrons move in that balanced equation is because at this point, we can only calculate standard potentials at 1 molar concentration. But if you have different concentration, we need a way to determine what is the true electromotive force or potential for that cell. and that's coming. Okay, so here's our overall balanced equation. And the voltage, the cell potential is 0.43 volts under standard conditions. We're going to calculate the actual cell voltage using a special equation called the Nernst equation. And believe it or not, that's a man's name. His last name is Nernst. Must be German. And not only that is, this reaction is spontaneous, but suppose we want to run the reaction in reverse. So we get copper metal and we change to iron. If we want copper metal, then all we have to do is apply a reverse voltage that is greater than the standard voltage or the voltage of the cell that we've determined. And that's called electrolysis. So you can run the cell backwards if you couple it with a source that produces a higher voltage than the spontaneous voltage. It's kind of like a potentiometer, only we push it harder. Potentiometer matches the voltage. Electrolysis exceeds the reverse voltage. All right. 10 o'clock. Let's see, where are we? Okay. We got a ways to go. 25, I can't do it in 25 minutes. We might have to ditch this lab. Okay. Well, it happens. Let's see. I'll leave that there for now. Okay, let's say we want to order the following from strongest to weakest oxidizing agent. So when we say oxidizing agent, that is the species that is reduced. All right. So if we have the strongest oxidizing agent, it is the one that is has the highest potential for reduction. Okay. So it would have the highest, the strongest oxidizing agent would have the highest standard reduction potential. That would be a positive value, or comparison, it'd be more positive than the others. Okay. So let's see. They're telling us they want to compare iron, sodium, chloride ion, sodium ion, and chlorine. Compare those and put them in order of strongest to weakest oxidizing agent. Okay, here's the problem. Some of them we have standard reduction potentials for, and some of them we don't. So here we're going to set up. So if we take fluoride, the fluorine has the highest reduction potential. So we know that one's going to be the best oxidizing agent. Chlorine has a value of 1.36 volts. And we're comparing these two, sodium and sodium plus. So the sodium plus an electron is minus 271. That's a relatively weak oxidizing agent. And then fluoride, oh, I'm sorry. Fluorine is not one of our choices. We're looking at fluoride. Fluoride would be the weakest, right? Because if we turn it in reverse, fluoride doesn't want, it's already got an electron. It doesn't want another one. Look at it that way. So its voltage is going to be very, very negative. Sodium ion, we're comparing these two. So this one does not want to be reduced. It's a metal. It wants to get rid of its electrons. Right? But this one does. Sodium ion does want some. Chlorine 1.36 and iron reduced. See here, iron reduced is going to be even worse. So sodium should be from, was it from least to greatest or greatest to least? Strongest to weakest oxidizing agent. All right. Why does it put sodium in there? Well, if the standard potential is minus 2.71, then going the other direction should be a positive, right? No, sodium is the weakest. Yeah, sodium is the weakest. Sodium ion is a good, is easily reduced. Chloride is better reduced than the sodium ion because it's 1.36 and this is only, well, that should be 2.71, shouldn't it? Right, you run it in reverse, it should be just change the sign. All right, let's see what my explanation is. So far, it doesn't make sense. Let's see, chlorine is a stronger oxidizing agent than sodium, but other species don't have standard reduction potentials to compare. Okay, we do have, okay, so chlorine is going to be a better, have a higher oxidizing agent is the strongest reduced. Okay, I was thinking in reverse. Yeah, chloride is has the highest potential for reduction, and then sodium has the next because they actually have values that are in the table. Sodium ion, excuse me, sodium ion. So chloride is better than sodium. And then iron, however, the remaining fluorine, sodium, and iron should not be easily reduced. Chloride is the strongest. All right. Let's skip that. I don't think that adds to the discussion, do you? It really just muddies the water. Probably I'll take that slide out. Let's go on to something that's more useful. Line notation. This is a shorthand. It's kind of like writing the electron configuration for an atom. It's a shorthand method of writing the galvanic cell. And with the cathode on the right and the anode on the left, the line notation is written the same way, with the cathode on the right and the anode on the left. But it's written such that the electrons move externally here and come in there and go from this to that. Whereas on this side, they go from this to make the electrons, they go like that. So show you an example. Let's see. We divide the two with a double line. This vessel is the cathode, this vessel is the anode. And the double line represents either a salt bridge or a porous disk. Okay. If we have a difference in phase, then we'll have a vertical line. For example, if we have copper strip on one side separated from copper ions in solution, that would be this vertical line separating the two. So what happens on this side? Well, say we have copper 2+ here and copper on this side, because the electrons are coming in here and changing that copper 2+ to this copper. And on this side, we're going from well, they're using magnesium there, aluminum and magnesium. All right, I messed up. Let's try this again. So on the right-hand side, aluminum is being reduced. Aluminum 3+ is being reduced to aluminum metal. Okay, we're tracking the flow of electrons. That makes sense. This is magnesium 2+, and this is magnesium. So the connection is between the metal electrodes, right? The connection here is between that electrode and this electrode. Okay, now it makes sense. This is in solution, and we're going to say this is aqueous, this is aqueous, this is a solid, and this is a solid. Now, if you're using anything other than standard concentrations, then you should specify them. Say, this would be 1 molar under standard conditions, but suppose we want to use 1/10 molar. And on this side, we could use 1/10 molar, or we could use 2/10 molar. Just whatever you select. Okay. And we like to use phases too. So with this being said, we can write this half reaction because this is the anode. In other words, magnesium is being oxidized. So we write magnesium yields magnesium 2+ and electrons. On this side, it's reduced. So on this side, aluminum 3+ plus 3 electrons is makes aluminum. But what if the electrode doesn't participate in the reaction, or the reaction itself occurs in aqueous solution only? Right, and we had that example earlier when we were balancing equations, half reactions. We had some that didn't have any metals in there, didn't have any solid electrodes. Right, so how do you get the connection? You use an inert electrode, because the reaction must take place at the electrode. If the electrode's not part of the reaction, then you just need something to move electrons, right? In your dry cell batteries, the electrode is carbon. Right? It's a graphite rod right in the middle of the battery. When I used to do this in the lab, for reactions that didn't involve the electrode itself, I would use platinum. Just platinum metal. It doesn't participate in the reaction, but it does convey electrons into the solution or out of the solution, whatever the case. But the reaction occurs at the electrode. Now, if one side of the half reaction equation is an ion in solution and the other half is also an ion in that solution, they make the exchange, the electrons move at the electrode. Okay, so here's an example where we have one side, the silver electrode, but we have iron 3 plus going to iron 2 plus in the standard reduction potentials. So which one do we need to change in order for this to be spontaneous? We make the 0.77 negative, right? And then when you add them together, you get 0.03 volts, positive volts. So that means that the iron 3 plus must be switched to the other side. So iron 2 plus yields iron 3 plus plus an electron. That's the anode. And the cathode remains the same. So we just change the sign from 0.77, add them together. And you get 0.03 volts. That's not a lot. But, the iron is not a part of the electrode. The electrode is not participating. So that means the iron side of the reaction, the anode, must have some inert electrode. Platinum would be a good choice. So there's an example. I mean, there's the diagram. See the platinum electrode on the left doesn't participate. Under standard conditions, 1 molar iron 2 plus and 1 molar iron 3 plus are in the reaction vessel. And that's where the reaction occurs on the aqueous ions at the electrode. So at the electrode, the iron 2 plus loses an electron, produces iron 3 plus, and that electron moves over through the silver and reduces the silver ions from solution, and they plate out on the electrode. Right? So what happens to the mass of that silver electrode? It goes up, right? And that's typical. When the electrode participates in the reaction, on the cathode side, its mass increases. If the electrode participates on the anode side, it's losing electrons, and the anode is going from solid to ion in solution. So the anode electrode, if it participates, decreases in mass. Okay? And right, we said this before, there have to be counter ions in there, right? That iron 2 plus and iron 3 plus, there have to be anions in there. Sulfate would be a good example. Chloride might work. Yeah, chloride would work. On the other side, I wouldn't want to use chloride though. Why? Because if you get chlorides moving to the other side, they're going to precipitate out silver as silver chloride. It's insoluble. So nitrate would be better because silver nitrate is soluble. I think silver sulfate wouldn't work either because silver sulfate is precipitates. And it's in your useful information. I think I still got that chart. Well, let's see. There's silver, chloride, bromide, iodide, sulfate, and all precipitation. So you need something like nitrate, probably a good choice as a counter ion, silver. So those are just practical things that you have to consider when you're trying to build one of these things. Line notation. All right. Line notation. So where's the solid? On the anode, the solid is platinum. Right? That's where the electrons leave the anode. And on this side, they enter at the silver electrode. Somebody's trying to call me. 800 numbers, probably spam. Okay. So then we would have silver +1 in the aqueous solution. How about on this side? Well, we have iron 2+ and iron 3+. If this is the anode, we're going from iron 2+ to iron 3+. Okay. Since there's no phase difference between the two, these are aqueous. We just put a comma. Okay. Let's see. Yeah, I got it right for a change. That's the line notation for this galvanic cell. This is just rehashing. Now, it makes sense that this formula would work. Once you've identified the cathode and the anode, then the value for the anode has to be flipped. It's no longer reduction, it's oxidation. So we change the sign. So it works. I just don't feel comfortable with it. Let's see. That's just a rehash. So this is a sketch of a silver and a copper cell. So which one's which? Well, the cathode's on the right. The silver is 0.8 and the copper is 0.34. So it would have to be the negative one, right? The copper would have to be the anode in order to give you 0.46 volts. And these are standard potentials, right? We haven't worked with the Nernst equation yet, but we're going to just in a second. Think about it this way. When you think of the concentration change, what does that do to the equilibrium? What would happen to the potential if you increase the copper concentration? Right? If you increase the copper concentration, then you are, let's see. Right. On the anode side, right? On the anode side, it's copper yields copper 2+ plus 2 electrons. If you increase the copper 2+ concentration, instead of making copper 2+ ions, now you're driving the reaction back toward the copper solid. That reduces the push from the copper side, and the overall voltage should also be reduced. And by the same token, if you decrease the concentration of copper 2+ on that anode side, it drives the reaction, according to Le Chatelier, it drives the reaction toward the right, as written. Right? That makes more copper, produces more ions, more electrons, and that should increase the voltage. Okay, does that make sense? Does now. Tell me about it later. Am I giving you a headache? All right, before we get to the Nernst equation, we're going to look at, we mentioned earlier, energy conversion from chemical to electrical. Well, if we're talking about energy, there's potential for doing work, right? Joules is an expression of energy, it's an expression of work. And we've looked at that in a previous chapter. The problem is if the cell potential, oops, maybe this will work. The cell potential is positive, then this is spontaneous. Right? But the value for work, if we look at our, remember our model, our system surroundings. if the cell potential is positive, that's going the wrong direction. Right? Because everything's relative to the system. And if the potential is moving electrons into the surroundings as a positive value, then what we're doing is we're reversing things, because that should be negative. If it's leaving the system, it should be negative. So if we're going to convert this to some kind of work, then the work has to be negative. So that means we've got to introduce a fudge factor. Right? So electrical potential, using this relationship, electrical potential is work over charge, Q for charge. Right? I know when we were talking thermochemistry, we used Q for heat, but now it's Q for charge. And if this is positive and work is negative, and Q is always positive, then we have to introduce a negative fudge factor in front of that. Negative times negative is positive. Right? So the, let's see, that's a mess. Negative work over Q is our, if we want to calculate work, right, then we have, put the Q over here, E times Q equals negative W. Or if we were going to calculate work, then work would be negative E times Q. Voltage times coulombs. Right, and coulombs equals joules per volt. So if coulombs is joules per volt, and this is volts, volts cancel, leaves us with joules, which is a unit of work or energy. Now this is the maximum amount of work. This is maximum. Right? We know we're never going to get the maximum. Right? That's an ideal situation. There are always losses somewhere. Okay. All right. Maximum work is the charge transferred for a given voltage. Okay, so think about how electricity is transferred from one place to another. Right? If it's going a long distance, you want a very, very high voltage so that the movement of charge is low to get the same amount of work. Now, there's another item to that component, and I'll show you in a second. I think I'm going to show you in a second. No, I don't. Okay, so let me introduce this idea. Let's see. Power transmission equals I squared. Okay. All right. Okay. Now I can talk about it. This is transmission of power. And power is energy per time per second. So horsepower is not the total amount of energy produced from your engine, it's how much can be produced in a second. Okay. So power transmission is this. Power losses are this. So what that means is if you want to reduce the losses in power transmission, you decrease the current as much as possible, because the power losses are based upon the square of the current, how much electricity is moving through. You want to reduce it so it's moving very slowly, but it's got a huge voltage, because because you want to transmit power this way. If you have a very large voltage, you can get power transmission with a lower. This is very high, this is very low, and you can get the same amount of power transmitted with the low current as long as the voltage is extremely high. You know, these power lines, some of them are a couple of 100,000 volts on the local county, but if you're going across the country, they're going to be 1 million, 2 million volts, right? To reduce the amount of loss by too much current. Okay. I'll have to cut out that dead air. Okay. So back to our topic. The maximum amount of work you can get from a spontaneous electrochemical process is negative voltage times the charge moved, the coulombs that move. The actual work is always less than that. Now here's our conversion factor. The Faraday is a measure of the charge per mole of coulombs. Right. And Faraday is named after Michael Faraday, who was an English physicist, chemist, who was actually self-educated. He was brilliant. In fact, his real claim to fame was when he investigated a new subject, he was a master at devising experiments that would give him the maximum amount of information. He was a tinkerer, so to speak. So the charge on 1 mole of electrons is 1 Faraday. So 1 Faraday equals 96,485 coulombs per mole of electrons. Okay. Okay. So remember when we just the last chapter we were in, what would be a spontaneous reaction for delta G? It would be negative, right? Negative. Right. And maximum amount of work would also be negative that we could get from a system, because it's leaving the system. So there we don't have to worry about the sign. The delta G equals the maximum amount of work that you can get. That's the free energy that's available. So the maximum amount of work then would equate delta G to a negative voltage times charge. Okay. Now, Q is in coulombs. And if we rearrange this, this is in coulombs. Excuse me. No, there's coulombs and there's moles. So if we move this over here and we abbreviate that N, remember that's what I use for moles, then Faraday times moles equals the charge in coulombs. So we substitute we substitute for Q this NF in Q, and we get NFE max. So the free energy can be converted to moles times the Faraday. Well, the Faraday is this unit here. So when we multiply it by moles, then we actually get the number of coulombs. Oh, there's Michael Faraday. That's when he was a youngster. Okay. So under standard conditions, the delta G equals a negative moles times the Faraday times standard potential. And since positive, let's see, where is it? Oh, I didn't write it. I didn't write it yet. So delta G equals NF E potential. So this is going to run in the direction in which this is positive, and that negative gives you a spontaneous delta G. So that's a useful equation. All right. Now, let's clear the board. There's this. I messed it up already anyway. I'll leave that there. It's our conversion factor. The other thing that we were going to do in the lab was create a concentration cell. If you have the same half reaction in both cells, then what's their standard potential? 0. Because you're trying to run one direction and run the other direction, and their potentials balance. So the voltage, the standard voltage for this cell would be 0. But if we change one of the concentrations, make one of them lower and the other one higher, usually anode is lower, then we can get electrons to move. This is called a concentration cell. All right. So what does Le Chatelier say about this reaction? Well, if the anode, right, the anode is the site of oxidation. So we're going to get silver in this case. Silver is going to yield silver plus an electron. And the cathode is going to be silver ions plus an electron yields silver metal. Okay. When we combine these two, what we need to do is designate which is which. So let's say this is the anode. This is the cathode. When we combine those two, then we get silver anode plus silver plus cathode yields silver plus anode plus silver solid. Cathode. Yes. Okay. So anode, cathode, anode, cathode. Now, if we're at equilibrium, and there's both standard concentrations, then what if we reduce the concentration? This is the spontaneous reaction that we want. We want it to go this direction. So how do you get it to go from left to right? The solids, remember, the solids don't enter into the equilibrium expression. So we focus on the aqueous solutions here, and here. If we decrease the concentration of silver ions, the reaction is going to move that way, isn't it? Okay. And that means it's going to move toward the production of silver at the cathode. Right? It's going to promote that reaction and move electrons from that side to that side. Okay, so that's why the anode is reduced in concentration and the cathode is always higher in concentration. That gives us a spontaneous reaction for a concentration cell. There's Nernst. They like those big bushy mustaches back then, don't they? A lot of people had them then. Nernst devised this equation that allows us to determine the true voltage of a cell based upon the concentrations in each of the anode and the cathode side. He had his fingers in lots of pies, and this was typical at the beginning of the 19th century. Scientists would be involved in various, they would cross over between physics and chemistry frequently. So he was active in thermodynamics, and his theories led to his getting the Nobel Prize in Chemistry for the third law of thermodynamics. So what's his Nernst equation? Oh, there's the third law. Totally perfect crystalline structure at absolute zero has zero entropy. That doesn't help us much, though, does it? Okay, so here's his equation. Is the actual voltage, the electromotive force, is based upon the standard potential, and then you subtract the gas constant times the Kelvin temperature over the moles of electrons moved in the reaction. So remember I said, keep track of how many moles move. I mean, when we put the two half reactions together, the electrons cancel, but they're still moving. So we need to know how many. And then times the Faraday. So that part is this part right here, that NF. And then the natural log of Q. So Q is the same thing it's always been. What is the actual concentration? In the balanced equation, calculate the Q for the actual concentrations. All right. So once you do that, then you can plug these values in here and find out what your true potential will be. So it's entirely possible that if the concentrations change and give you a Q here that produces a negative E, then at those concentrations, your galvanic cell is going to be non-spontaneous from left to right. So that means you'd have to flip the cell to make it spontaneous. So it may be spontaneous under standard conditions, but not necessarily under actual conditions. Now, there's a modification to this equation. If we set the temperature at 25 degrees, standard temperature, and we take the value of R, which in this case, since it's energy units, it's 8.3145. And standard for temperature would be 25 plus 273 is 298. So if we multiply that one times that one, and include the Faraday, which is also a constant, then we get a modified equation, which is a little easier to work with. So under conditions of 25 degrees, 25 degrees C. Then E equals E0 minus 0.0591 divided by the number of moles of electrons that move times the natural log of Q. Now, this is more useful for variable temperatures. But if we're at standard temperature, then this one works just fine. Oh, excuse me. My mistake. Common log. Not only do we change this part of the reaction, we change this part from natural to common log. Common log sometimes is easier to work with. And that box on the right just proves that the conversion factor that I introduced. You don't have to know that. Okay. So at 25 degrees, and the equilibrium, Q equals K. So what also occurs at equilibrium? No voltage, right? No electrons are going to move because the overall equation is stable. So what do? Is this useful? Well, yeah. If we take this one right here, right, we say the actual voltage is equal to 0 at equilibrium. But under standard conditions, there is a value, right? And 0.591 over N times common log of K. So if we know the number of electrons moving and we know the standard potential for our reaction, then we can calculate the K. So there's another connection, right? Last chapter we determined how to calculate K from our entropy, and now we can do it from electrical potential. Right? Okay, so I didn't finish deriving this equation. So if I move E to this side, now it becomes negative E, because that's a 0. And that's negative 0.0591 over N log K. Well, negative on both sides. There you go. So if we know the E0 for our reaction, and we know the number of the moles of electrons that are moving, then we can calculate the K for that reaction. Okay. Let's see. So we're taking this, let's see, S2O3 is thiosulfate ion on the right-hand side. I'm not sure about the one on the left, what to call that one. But if we take this reaction and we split it into two half reactions, and we can calculate the E0 from those values, right? Which one do we flip to get a positive? Well, the bottom one. The bottom one becomes the anode. So the E0 for that one would be 67, 0.67 volts. Okay. And then we have 0.0591. We're missing the number of moles of electrons. All right. So how many electrons move? Well, if we balance it, we need two moles of electrons, don't we? Right. We have to multiply the bottom one times 2 after we flip it. So this is 2 down here. That's log K. So now we can solve for K. There it is. And n equals 2. Okay. There's our equation. Log K equals 22.6. Log K equals 22.6. So what do we do? Anti-log of 22.6. It's 4 times 10 to the 22nd. And that's typical for spontaneous electrochemical reactions. The K is extremely large. It's huge. Okay. Concept check. When E, what's the relationship, the difference between E and E0 when E is equal to 0? Well, if E is equal to 0, we're at equilibrium, but E0 will be a positive value. That's a dead battery. We're at equilibrium. And when E0 is equal to 0, we've got a concentration cell. Right? Now, the E value might be different as long as the concentrations are different. Right? You'll have a value, usually in millivolts. But the E0 is 0. All right. So let's see, what do we have here? Concentration cells constructed using 2 nickel electrodes with Ni2 plus concentrations of 1 and 1 times 10 to the minus 4 in the 2 half cells. So the anode is going to be the low concentration, the cathode is going to be the high concentration. And if we write the equation so that we have the cathode plus the anode solid equals the cathode solid plus the anode ion, then we need to calculate Q. Right? So Q is just the ratio of the anode concentration to the cathode concentration, right? Because the solids don't count. And if we plug those values in, the anode is 1 times 10 to the minus 4, cathode is 1, and we work that equation out and we get a voltage of 0.118 volts, which is 118 millivolts. 6 of one, half dozen the other. Okay, let's see. Another concept check. We have a nickel electrode in 1 molar nickel, and we have a silver electrode in 1 molar silver. Sketch the cell. All right, which one's going to be the anode? Which one's going to be the cathode? Well, which one did we have to flip? We had to flip the nickel. That's the anode. So if we draw that, oh, that's the line notation, excuse me. So the line notation is going to put the nickel on the left-hand side, and the solid, the electrode goes on the outside because that's the connection external to the electron movement. That's the way I look at it. So that would be the line notation. What's the cell potential? Well, this is also the diagram. I got this program that'll let me do that. Silver's the cathode, correct? Nickel's the anode, correct? We've identified the solution contents. Nitrate is our counter ion. That makes sense since silver's involved. And the salt bridge is going to have sodium and nitrate in it. So we wouldn't want to use potassium chloride like we were going to do today. Right? That would be a no-no. Okay, let's see. We already calculated that, didn't we? Nickel and silver? Yeah. Is that what we did before? Yeah, that's what we did before. Okay, so there's our voltage. Our standard voltage is 1.03. All right, we'll talk a little bit about batteries and then we'll talk about electrolysis and we'll be done. Let's leave those there. So, the galvanic cells that we produced up to this point had separate containers with a salt bridge. That's because the electrolyte, right, the liquid in which they're submerged, was different for each one. In the lead acid battery that's under the hood of your car, unless you have an electric vehicle, but that lead acid battery has electrolyte in common for both of the cells. So we can submerge, as long as we keep the plates separate, we could submerge the two plates of the lead acid battery in the same solution, which is a sulfuric acid solution. One plate is lead and the other one is lead-4 oxide. Okay, the cathode is lead-4 oxide and the anode is lead, pure lead. Let's see. Am I going to give you the, overall reaction? Here we go. So the overall reaction here incorporates sulfuric acid and it produces the same product at both electrodes. So at the lead electrode, it's going to have lead-2 sulfate deposited on its surface. And at the lead oxide, it's going to have lead sulfate deposited on its surface. Okay. That's the problem. Because remember, the reaction occurs at the electrode. So if you've got an electrode here, whether it's lead or lead-4 oxide, if you have lead-2 sulfate deposited on the surface, right? And you want to run that cell backwards, right? You discharge it, get electricity from the anode to the cathode. If you want your alternator to recharge the battery, it's got to run that reaction in reverse, which means it's got to convert lead sulfate, the lead in lead sulfate, to lead oxide, lead-4 oxide, and the lead in this lead sulfate to pure lead metal at the surface. Well, if you've got too much lead sulfate on the surface, the electrolyte can't reach the surface for the reaction to proceed. So what you've done is you occluded the electrode and now it won't recharge. That's what we call sulfating out. At that point, you cannot recharge your battery. You got to just junk it and let the recyclers deal with it. And that goes into the engineering of the battery plates. They can be constructed in such a way that the deposits of lead-2 sulfate are more diffuse on the surface. And that allows the electrolyte to get in there and complete the reverse reaction when you want it to. It also gives you more current. It gets you closer to W max with the proper construction of the electrodes. If you just use a plain old plate, which is the way they used to make them long time ago, your batteries would be good for a couple of years and then they'd be unchargeable. But now you can go 5, 6, 7 years, and your battery's still doing its thing, recharging. Okay. So the point here, that's the long way around. The point here is you don't need a salt bridge because the half cells are submerged or have the same electrolyte, the sulfuric acid. That's one of the advantages. Now, used to be your batteries would have 6 caps on the top and they have little tiny pinholes in them. If you overcharge your battery, it's going to produce hydrogen gas. And you don't want it to accumulate in your battery because it could blow up. So they have those little vent holes in it. Now you can seal your battery because they have modified the technology so that it won't overcharge, or if it does overcharge, the hydrogen gas is absorbed and it's not explosive. But you have those 6 cells because each one of those cells one, two, three, 1, 2, 3. Each one of those cells is connected in series. So that, and this is one of the laws of physics. If you have a potential here of 2 volts, which is nominal for this, for each one of the cells. You have 6 cells, you connect them in series, you add up the voltages. So 6 times 2 is 12 volts. That's how you get 12 volts out of that battery, is you connect these in series. It's one of Kirchhoff's laws. If you ever take physics, you'll get that. Otherwise, you can just use it in parties to amaze your friends. Okay, here's the dry cell battery. Now, dry cell is a misnomer. If the cell were completely dry, there would be no reaction because you can't get the ions to move. So it's actually a paste. It should be the common paste cell battery. And the cathode is that graphite rod in the middle, because the site of reduction is at the cathode, at the graphite rod, but the reaction itself is not the graphite rod. It's the mixture in that paste occurring at the rod. And the anode is the case of the battery. If you ever have an opportunity to remove the plastic film on the outside of your battery, you'll get a zinc shell. That's the anode. These are generally meant to be used once and thrown away. These are not rechargeable. Now, it doesn't mean you can't recharge them. It's just that not very efficient. Right. Okay. So that's the point in the dry cell battery, is it's one of those reactions where you need an inert electrode at the cathode in this case, because it's not involved in the reaction. This is a mercury battery. We don't use them anymore because of the mercury, but there's a mercury 2 oxide is in that paste, and the anode is a zinc container. So it's I think the connection is the cathode is not participating in the reaction. Yep. So that steel there is just the connection for transferring electrons. So now we use something else similar to that. That looks like maybe a watch battery, or if you make it small enough, it would go in your hearing aid or a calculator. But there's a different technology that we use. I think it's not listed here. Trying to think. What do they substitute for that now? Silver? I think they use silver. Okay. Here's a different type of battery. It's called a fuel cell. The advantage of a fuel cell is you don't have to recharge it. It's more like a gasoline engine, right? If your car's got a fuel cell in it, and you're driving down the road and the indicator says you're getting low on fuel. In this case, the fuel is hydrogen. You're getting low on that, you stop at a service station, which is hopefully set up to do it, and you just refill your hydrogen tank, and you're off and running. But it is an electrochemical process, so it's driving electric motors to your wheels to make them run, and the power is coming from this reaction where we take oxygen from the air, hydrogen that we're supplying into this fuel cell, and they're combining to make water and releasing electrons that are used in an external circuit to run your electric motors or to charge batteries. Okay. Now, this is not the only type of fuel cell, hydrogen oxygen. It was the fuel cell that was used in the early space program to provide electricity for the capsules, because there was plenty of oxygen there, right? They had oxygen tanks for the astronauts to breathe. All they had to do was add hydrogen. So they had a hydrogen tank and then fuel cells. Originally, the fuel cells were not very efficient, and they had to be run at very high temperatures. So that made them unsafe. The temperatures for running those cells have come down. In fact, I think they've got some engineering advances that produce room temperature fuel cells. But still, the problem is not just the technology to get the energy from the electrochemical reaction. It's how do you pack enough hydrogen in a car to run 400 miles? Because hydrogen is a problem. If you put it in a compressed tank in your car, that's an explosion hazard. If you get in a wreck, right? Those things will go up to 2,500 pounds per square inch, right? And they go off like a rocket if you hit them with another vehicle. So they need some other way to get that hydrogen in there that's more stable. And they use some types of, they have the tank and it's filled with something, right? High surface area, a zeolite maybe. And it just absorbs the hydrogen to the surface. And then all you have to do is open the valve and it comes out by itself. Now, it doesn't store as much hydrogen. That's another problem. But it still works and it's safer. Okay. Now let's talk about electrolysis. First, actually not electrolysis yet. Let's talk about a galvanic cell that we don't want. And that's the type of cell that produces corrosion. In other words, it takes the metal that you don't want to degrade and turns it into an anode. So you're extracting electrodes from that metal and turning it into various things like oxides or sulfides. For instance, you would go from, say, iron, metal, and oxygen from the air, and you produce there, iron trioxide. That's rust. Okay. This is called corrosion. And in that case, what's being oxidized? Iron. It's going from 0 to 3+. And what's being reduced? Oxygen is going from 0 to -2. Okay. So this is an example of corrosion. I don't know if I mentioned this before. I used to live in Atlanta. I grew up in Atlanta. And they had a hockey team, right? The Atlanta Flames, for a while, right? And they wanted an arena. So they got an architectural firm to design a multi-purpose arena. So they could have basketball in there, they could have hockey games, and a number of other things. And this firm decided and convinced the banks and the owners that it would be wise if we could build this thing out of a material that wouldn't need to be painted ever. Right. And stainless steel is pretty expensive. Right. So they said, all right, we got an alternative. There's this new form of steel. It's not stainless, but it's really cheap. And it's made so that it will go from iron to rust so fast that it coats the surface and keeps water and air out. Right? Just like stainless steel does. That's what primarily chromium. We mix chromium with iron, and that gives you stainless steel, along with some carbon. But it turns the metal kind of a brick red on the surface, right? And it works, right? It keeps the air and water out. And the problem is rust is density, right? You have a certain density here for the iron, and the density here for the rust is much, much less. So in order to, it expands, right? And if you've ever seen an old car, an old tractor out in the field, and you look at where the steel used to be, it's just like these big flakes coming off of it, right? That's because as it rusts, it expands and flakes away from the metal and exposes it underneath. So eventually it's all gone. Well, they didn't count on that. They built the building and covered it with this steel, and within a short time it turned brick red and it looked great. You know, it stood out among all these white buildings. The problem is Atlanta gets, I don't know, 45 inches of rain a year, and as soon as it rains, it sloughs off, right? Because it's less dense, it separates from the surface. It sloughs off that rust and it runs out across the concrete and makes these red streaks everywhere, and it is ugly. So they put up with it for a few years and eventually tore the building down. Okay, that's an example of corrosion. Something you don't want to happen typically. This is what happens to the surface of steel or iron of some kind. It sets up itself as a small galvanic cell on the microscopic level, right? And the anode is where you see the pit forming, and the cathode is over here where the rust is forming. Okay. So that's why keeping moisture away from the metal, the iron, is good. So we paint it, right? We just exclude everything. The other way is you can coat it with something that's more reactive than iron, like zinc. So that's where you get galvanized buckets. That used to be the only kind of bucket you could get, was a steel bucket that was dipped in zinc, right? Galvanized buckets. Now they make them out of plastic, or they paint them, or they powder coat them with enamel and run them through the furnace, and you get this rock hard paint on it. You can barely scratch it. Anyway, so that's an example of corrosion of iron. I mentioned one way to prevent it is to paint it, or you can plate a metal on the surface, right? Steel bumpers on cars used to be chrome plated, right? And if you go to an antique show, you can still see some chrome plate bumpers. Now we don't have any of them. They're all plastic with a steel infrastructure underneath. But they would take the steel and they would put it in this solution of chrome, and they would reduce the chrome from its ionic form to its metallic form at the bumper, and it would plate out on the bumper. Now, it's a little more complicated than that, but that's all the explanation you probably want to hear. or you can galvanize it, right? Just dip it in molten zinc, or you can form an alloy. And stainless steel is an alloy. Originally, the story behind the creation of stainless steel spans decades. But originally, it was in the neighborhood of 35% chromium in steel. So that's a type of alloy that protects the steel. Or you can protect it cathodically. And when fuel tanks and pipelines, well, pipelines are still made of steel, but fuel tanks are more often now made of structural plastics. But when they were made of steel, they would rust, and that would be bad because you'd start getting holes in your tank and the gasoline would be leaking out everywhere. So they protected the steel by attaching a wire to it over to a big chunk of magnesium or zinc. And those would be the sacrificial anodes. In other words, they would corrode, and as they corroded, those electrons would be supplied through that wire to the steel tank and keep it from rusting. And pipelines are like that now. Well, now the pipelines are wrapped in some polymer, right? They just eliminate water from the surface now. They don't bother with anything else. So there's cathodic protection. The cathode is actually the steel pipe, and the anode is the magnesium, because it is the site of the corrosion, the oxidation. Okay. Have you ever seen buildings or statues or whatever that are made of copper? So copper roofs are common, especially in Europe. And they eventually form this, what they call a patina. It's kind of a bluish green color. Well, that's corrosion of the copper with oxygen and sulfide in it. And when it does that, it doesn't have this density problem. So when it does that, it forms this permanent layer on the surface, and it gradually goes deeper, and then it stops and forms this beautiful color, but it doesn't corrode any further. Okay, coatings, alloying, we talked about, cathodic protection. Right, the buried pipe is the cathode. Now let's talk about electrolysis. If you want to run the reaction backwards, right, the non-spontaneous direction, what you have to do is introduce a voltage in reverse. Am I running out of time? Oh, you have to run the voltage in reverse to the spontaneous direction, right? You can balance it. If you balance it exactly, then you've got a potentiometer. But if you increase the voltage just slightly above the spontaneous direction, you can drive the reaction backwards. And that's what we do in our car batteries. The alternator produces alternating current, and then we have a rectifier in there that changes it to direct current, and that's sent to the battery and keeps it charged. And then chrome plating bumpers. That's electrolysis also. We're driving the reaction backwards to what it normally would be. Here's an example I like. I've written this reaction in terms of hydrogen combining with oxygen to burn and shooting the space shuttle into orbit. Well, go the other direction. You can take water and run a voltage through it, and you can electrolyze it. In other words, you can drive the reaction backwards, the non-spontaneous direction, and produce hydrogen and oxygen. And that's, in fact, the holy grail of a hydrogen economy. Right? We've got lots of water on this planet. What we need is a cheap source of electricity, and we can produce enough hydrogen for a hydrogen economy radial economy. But we don't have it yet. What we really need is fusion power. And we can get unlimited amounts of energy from fusing hydrogen from water and use that energy to electrolyze water to make more hydrogen. That's probably never happened in my lifetime. As I'm on the downhill slide now. Okay. The other problem is engineering and economics. Right? If we can get a cheap source of electricity to electrolyze water to form hydrogen, then you've got to get it to the user. And we could probably retrofit natural gas lines to transmit hydrogen. That wouldn't be a problem. But for vehicles, you have to have stations, just like gas stations now. You'd have to have hydrogen stations or whatever we're going to use in our fuel cells. All right. There's a stoichiometry for electrolysis that is useful. And we're going to be using that conversion factor, the Faraday, to do this. So if we want to know how much, in this case copper, but let's say we're chrome plating a bumper. We want to know how much chrome in grams we can deposit on that bumper if we supply it with a certain current for a certain number of minutes. How much will we plate on that bumper? And we can do this stoichiometric calculation. What we need to know is what's the current, coulombs per second, which is an ampere. 1 amp, which is abbreviated A, is equal to 1 coulomb per second. So if we know the number of time, the amount of time, we can take whatever the amps is, multiply it by the time in seconds, and we can get the charge. How much charge is transferred in the process. Then we use our Faraday to convert the charge to moles of electrons. Then we use our balanced equation to say, if we have a mole of electrons, how many moles of reduction can we do? And then we take that moles of reductant and convert it into grams. So that's the logic behind. And you need that conversion factor, 96,485 coulombs per mole. I think I've got that in the useful information. I'm pretty sure I do. I better have it because I can't remember that number all the time. So let's use that to solve this problem. So we're given an unknown metal of some kind. Right? And we're going to electrolyze it from its from this solution, this metal and nitrate. So what does that tell you the ion is? The ion is 3+ charge, right? Because each one of these is a -1, that has to be a 3+. Okay. So how are we going to turn it into the metal? Well, we have to reduce it with 3 moles of electrons for every mole of metal. Right? So there's your stoichiometry right there. Now, if we have 52.8 seconds of current at 2 amps, so the current is 2 amps for 52, and the time is 52.8 seconds. And it plates out a mass of 0.719. What's that? 0.0719 grams. We want to find out what the metal is. Okay, how do we do that? Remember, there's only two ways. You have to know the atomic number, or you have to know the molar mass. Molar mass is our best bet for this one. Molar mass, or what I call molecular weight, is mass per moles. Okay? So, if we're sending 2 amps through that, it's 2 coulombs per second. Right? How many seconds are we going? We're going 52.8 seconds. Okay? So that cancels the seconds. How do we get rid of coulombs? Because we need moles of electrons. So it's 90, what was that? 96,485. 96,485 per 1 mole of electrons. Okay, so that gets rid of coulombs. Now, moles of electrons, we want to moles of metal. So what's the ratio? Well, 3 moles of electrons for each mole of metal. So that tells us the moles of metal corresponding to that mass. Then we can plug it in up here. So need a calculator for this. Let's see, 2 times 52.8 divided by 96,485. Oops, I messed up. Gotta go back again. 2 enter 52.8 times 96,485 divide and 3 divide. So that's equal to 3.648 times 10 to the minus 4th moles of metal. And the molecular weight then is mass 0.0719 grams per 3.648 times 10 to the minus 4 moles. And 0.0719, divide that into it. That's 197 grams per mole. So we go to our periodic table. Woo, we just plated out some gold. Okay.
And that conversion isn't in useful information.
Oh, the value.
You have Faraday in there, but you don't have that one.
Oh, wait a minute. It's got Faraday?
Yeah, it has Faraday. Second column.
There it is. Yeah, that's it. That's the
Okay.
conversion.
Okay.
Yeah. That's 96,485 coulombs per mole. Philip. That's what a Faraday is.
Okay.
Are we done? Oh, no, we're not done. Let's see. We're getting there. Okay. So that's using electrolysis to identify an element. And that's what they do to cheap jewelry. They just plate it with a very thin layer of gold. And it's good for a while until it wears off and then finger turns green. Okay. Consider a solution containing 0.1 molar of each of the following: lead, 2 plus, copper, 2 plus, 10, nickel, and zinc. Plus. Okay. 0.1 mole of each one. Predict the order in which the metal played out as the voltage is turned up from 0. Okay. So if we're going to plate them out, they have to be reduced. To yield the metal for each one. Now, since each one of these, since they're all at the same concentration, then we can use their standard reduction potentials to predict what's going to happen. If they were at different concentrations, that would be more complicated. So let's see. Where's our table? There it is. There's one. Yeah. Right, you got to tell me. What's the standard reduction potential for lead 2 plus to lead?
Negative 0.13.
Negative 0.13. Okay. How about copper 2 plus?
0.16.
0.6. Okay. 10 2 plus?
Negative 0.14.
Okay. And nickel 2 plus?
Negative 0.23.
And zinc 2 plus?
Negative 0.76.
Okay. That's a positive. Okay, as we turn the voltage up. So what we're doing is this is the spontaneous direction. Let me see if I got mine. Yeah, okay. So this is all in solution. And we're going to plate these out. This says that the spontaneous direction is that way. So it's going to take greater than 0.13 volts to plate this out. Right? And this one, it's going to take greater than 0.14, greater than 0.23, greater than 0.76. So the first one that's going to plate is this one, copper. Because it's already spontaneous in that direction. So copper 2 plus is going to plate first. And then the next one is going to be the next voltage above 0.
But
Lead. Yep. Lead 2 plus. And then 10 and zinc. Oh, excuse me. Yeah, you're right. Nickel. Okay. And then zinc. So is that 1, 2, 3, 4, 5? Right. So let's see if I got it right. Okay, they form at the cathode. Reduction potentials will predict the order of plating. The more positive plates first. Copper, lead, tin, nickel, and zinc. Yep. It's gratifying when you get it right. Okay. Other electrolytic procedures that are commercially significant. During, let's see, when was it? It was after Napoleon. Yeah. The French Revolution collapsed the monarchy. in about, well, it was over several years, about 1790. Let's see. That wasn't 90. It's in the 1780s. French Revolution. Collapsed the monarchy, and then the reign of terror started. They started chopping people's heads off. And you got nothing but chaos. So when you have chaos, usually people want stability. So that was Napoleon's cue. I'm going to come in and stabilize the situation. So he got his army together and he took over the country. He said, now you have a stable country. You also don't have any rights either. And then his big mistake was he didn't stop at France, right? He tried to conquer all of Europe. But after Napoleon was sent to, let's see, Sardinia. No, it was one of those Mediterranean islands. He was exiled. The country went back to a king for a while, and they had what was his name? Need to ring the history professor and ask him. Can't remember. Anyway, it was state dinners were common even before for the kings and for our president, for anybody. State dinners were there to entertain visiting dignitaries. They didn't use gold flatware or silver flatware. It was too cheap. They used aluminum flatware because at that time the production of aluminum was more expensive than gold because it was produced by chemical means. But of course, things have changed because now we wrap our food in aluminum foil and we throw it away when we're done. It's cheap. The reason it's cheap is due to two chemists. Hall, I can't remember his first name. Hall was very young. I mean, right out of high school and into college, he was interested in making cheap aluminum from the ore. The ore is called bauxite. And in fact, he set up a laboratory in his parents' garage and made a huge mess. But eventually, he knew what he had to do. He knew he had to use electrolysis to form the metal from the aluminum ions contained in bauxite. The real problem was two things, actually. Was a source of power with enough voltage to do the job, and getting the aluminum into solution, aluminum oxide into solution, because the melting point of aluminum oxide is over 2,000 degrees. That takes a lot of energy. So he and Hérold, who was French, and they were both working independently. So they're both given credit. Hit on the possibility of combining aluminum with this other cheap available material called cryolite. It's sodium aluminum fluoride. When they did that, they cut the melting point in half. So now if you could efficiently melt aluminum oxide, and you could still electrolyze the aluminum because now it's free ions. And they used carbon graphite rods at the cathode. And when the aluminum was converted to aluminum metal, it just settled out, right? It's a solid. So it settled out. It's still molten, but it settled to the bottom of the container. And when the process was finished, they just knocked the plug off the bottom and out came this pure aluminum. Every once in a while, you had to replace the carbon electrodes because the heat would deteriorate them. But this was the process that made what you need is a cheap source of electricity. So that's why Alcoa put one of its plants right in smack dab in the middle of coal country in Pennsylvania, because at that time coal was cheap, and it was on a waterway, so they could get their bauxite from the Caribbean, Puerto Rico. They could just dig it out of the ground and send it up the Mississippi and Ohio and across into Pennsylvania, and you got your cheap source of electricity from coal-powered plants. The other way you do it is you go up the Ohio and into the Tennessee River, and you get cheap hydroelectric from the TVA, Tennessee Valley Authority. Both of those contributed to the cheap electricity that would allow the cheap production of aluminum. You can replate your spoon. I've got a set of flatware at home that's silver plated. I was helping out, our church was cleaning out a storage building, and they don't use this flatware anymore. They use plastic. So whoever was in charge, one of the elders, I think, said, "We're just going to throw this stuff away." It says, "Don't do that. I'll take it home." So I had this silver plated flatware in these felt wrappers, and I took it home. And all you have to do to replate it is electrolyze it with silver, if I wanted to do that. Usually though, with silver, with sterling silver flatware or with silver plate, anyway, you can spontaneously convert the corroded silver on the surface into silver metal. All you have to do is get a glass baking pan, and you put aluminum foil. Oh, excuse me. No, you can't do that. It has to be aluminum flatware. But if it's aluminum, then you put water in here and salt, and you just lay your flatware there if it's aluminum, and it will convert the corrosion from aluminum oxide to aluminum. Actually, it will work on silverware. You know why? Because aluminum is the anode and your flatware is the cathode. So the silver, the silver, corroded silver is converted into silver metal by corroding the aluminum. Oh, so I was right. It will work. I knew it would work. Just had a momentary glitch. Oops. This is the last one I want to show you is the industrial uses of sodium and chlorine. Sodium metal and chlorine gas are numerous. I mean, they're just they spread throughout the industry, chemical industry. And this is the way they produce chlorine gas and sodium metal. They electrolyze it. Right? They drive a direct current through molten. Well, they mix sodium chloride with calcium chloride. Sodium will, this reaction occurs at a lower voltage than this reaction. So if you control your voltage, you can keep the calcium in solution and turn the sodium into molten sodium metal. But by putting calcium chloride in there, you reduce the melting point, just like we did for aluminum. And then at the, let's see, this would be at the cathode. And then the chlorine
right? Molten, so that's liquid. Yields Cl2 gas plus electrons.
This would be at the anode. Right? So the chlorine gas is easy, it just comes off. And you can pump the liquid sodium out. So what are they good for? Well, if you take chlorine gas, you take the sodium, combine it with water, and it makes sodium hydroxide. Right? Then you take that chlorine and you bubble the chlorine back through it. And that makes sodium hypochlorite, bleach. That's just one of the things you can do with it.
Okay,